Welcome to Introduction to Geology. I'm Dr. William Patterson. Today we will be talking about metamorphism, alteration of rocks by temperature and pressure. This is part 2 of 2 in which we will discuss textures and grade as well as plate tectonics and its role in metamorphism. And as a bonus, we'll take a couple mini field trips to Wales and the nicest place on Earth, Greenland.
Let's rock.
Metamorphic textures include size, shape, and arrangement of minerals. Directed pressure causes sedimentary rocks such as shale to form cleavage planes that may be different from their original bedding planes. So in this example, this rock has been tilted at a, say, 40-degree angle, 40-degree angle from its original horizontality. So this original horizontality is now angled at 30 degrees, 40 degrees, and the rock is compressed from the left and the right. This compression results in slaty cleavage planes. The rock is going to split like this along these slaty cleavage planes as opposed to splitting along the bedding planes. Foliation is the most prominent feature of regional metamorphism. A set of flat or wavy parallel cleavage planes is going to be produced by deformation under directed pressure. So here, like the shale, we have original bedding represented by these bands, light-colored bands and dark-colored bands. Compressing this material from side to side is going to result in a transition of the orientation of the minerals. They're going to rotate from lying horizontally to perpendicular to the compression. And this is known as foliation. Essentially, it means leaf formation or leafification, like leaves of a tree or playing cards. Characteristic minerals include staurolite, quartz, micas, and pyrite in this case. So we're taking a shale and a sandstone or a sandy shale, and we're squeezing it from the sides. That's going to rotate the minerals within this rock, or it's going to re-precipitate them with this new orientation. Taking a closer look, we see that foliated rocks contain platy minerals that are aligned along a preferred orientation. So the micas and the staurolite crystals are all going to line up perpendicular to the forces. And just taking a further closer look, foliation is going to be the result of these compressive forces. The minerals become elongate, perpendicular to the compressive force, or they may rotate into that new position. Quartz being relatively equant doesn't play the game very well. Feldspars are a lot better. Minerals like staurolite and micas really get in line to take this new foliation. And here we see a closer look at the previous diagram, where the original bedding can be seen as thin sandy or silty layers between clay minerals. So the material was deposited vertically, oldest here, youngest here, and then subjected to pressure from the sides, not from above and below principally, but principally from side to side. And this is going to result in the generation of these foliation planes. So this is generally the result of regional metamorphism, which is generally the result of plate tectonics. So this results in a preferred orientation of crystals and the characteristic slaty cleavage. Foliation is a dead giveaway, this type of directed pressure metamorphism. As metamorphic textures are driven by metamorphism itself, the intensity of metamorphism is going to drive crystal size and the coarseness of foliation, with increasing intensity of metamorphism leading to increasingly large crystal size and increasingly coarse foliation. Starting from low grade to high grade, we see the metamorphic rock slate. This is basically a baked shale. It has a dull surface. It does clink when you hit it with a hammer, as opposed to slate, which is a doot thud. Stepping up in crystal size, we have phyllites. You can think of a phyllite as a shiny slate. And the reason it's a shiny slate is because very small mica crystals are forming to give it this sheen. Schist displays abundant platy minerals and generates the optics known as schistosity. If we further increase the temperature and pressure, we develop larger crystals with fewer platy minerals and this characteristic banding of a rock we call gneiss, cranking up the temperature to just about melting the rock. In fact, just a little bit of melting does occur. We generate what are called migmatites. These are kind of the swirly looking, toothpastey, those multicolored toothpastes. Squeezing that out of the tube, you get a rock that is known as a migmatite. So taking a look at these foliated rocks, Foliated rocks are one branch of metamorphic rocks. Non-foliated rocks are the other. We'll cover foliated first here. Foliated rocks are defined by the degree of cleavage, the degree of schistosity, and the banding. So again, slate is the lowest grade metamorphic rock, generally colored by organic matter. Lots of organic matter means dark slate. They're used for pool tables, blackboards, flagstone, and roofing tiles traditionally. A phyllite has a glossy sheen due to small mica crystals at the surface. Both slate and phyllite display slaty cleavage, an easy to split rock. A schist is defined by schistosity, a coarse, wavy foliation that results in a very shiny surface. A gneiss displays coarser foliation due to segregation of light and dark-colored minerals. These are high-grade metamorphic rocks. Migmatites, the highest grade, the highest of the high, are a mixture of igneous and metamorphic rocks due to partial melting. So it's mostly metamorphic, but with some melting, that implies igneous. Therefore, it's a mixture, a true mixture of igneous and metamorphic rocks. Taking a look at some real-world examples, this is the Tintagel Old Post Office. It was originally built as a farmhouse in the 1300s, renovated in the 1600s when they put a slate roof on, and again in the 1700s they added a chimney, which means bedrooms could be added. The smoke is no longer filling the structure entirely. That's the way it used to be. In the 1800s, it was nearly torn down. It was kind of falling apart. Some rich artist bought the place, renovated it, and thanks to their efforts, it's still there today. So this is a structure that's been around since the Middle Ages. Moving into Wales, sort of the center of slate production in Europe, since the Roman times, we have some slate workers splitting the rock by hand on its slaty cleavage. Slate dealers here in the busy slate market. This is located in Wales, and a close-up here of this portion of Wales. What we're looking at in these rocks, the next few pictures, are going to be Cambrian shales. And what this guy is doing is signaling to the workers, "Minnan all girth, get back to work, slugs." So here we have the world's worst train experience. This is in Wales, which is known by the Welsh as Cymru. That's the real name. Wales actually means foreigner, so no one calls themselves the foreigners. This is in Llanberis in Gwynedd, North Wales, and it's an old slate mine that's now a tourist attraction. So to amuse us as tourists, they still operate these slate locomotives that are coal-powered on a narrow-gauge cog railway. If you've never experienced a cog railway, consider yourself fortunate. So here we have the cog railway, the passenger car working its way up the mountain. This is the engine in the back. You can, if you're lucky, you'll get this engine that was made in 1889. It's particularly stinky and slow, clunky. And the way these cog railways work is a gear basically turns on this cog track. So just imagine a coal-powered engine that's turning this gear on these cast iron tracks going up the mountain. Because it's narrow gauge, we had to get out of the carriage when the wind speed picked up so that it didn't actually blow off the mountain. The disadvantage of a narrow gauge railway. So this was used for a considerable amount of time, used for over 50 years as a means to transport slate from the slate mines up near the top of these Snowdonian mountains back down to a shipping center below. So what they've done is taken some old cars and made them particularly uncomfortable. Somebody asked me, "What's the train like?" And I said, it's like stuffing yourself into a metal garbage can with some bowling balls and rolling it down a hill while somebody beats it with a baseball bat. Not for everybody. For some reason, I forgot about visiting in the 90s. I got on the train again. Immediately, I remembered, oh no. It's a really uncomfortable experience if you're more than 5 foot tall. And here's the railway as it proceeds on up to the mine. We didn't make it up here because, again, the wind was going to blow us into this canyon, which in Welsh is known as a cwm, C-W-N. Proceeding upgrade in metamorphism, we have a phyllite. Again, the glossy sheen is due to micas, so the difference between a phyllite and a slate is going to be whether the rock is shiny. Otherwise, they split in a very similar way via rock cleavage. Rock cleavage is different from mineral cleavage. It's the way a rock splits rather than the way a mineral splits. Schist takes the shininess up a notch. These are very, very shiny rocks, and it's because the mica grains are much larger. And most cases, muscovite gives it this sheen. They're also notable for these porphroblasts. In this case, these porphroblasts are garnets. So here we see a schist that displays the crystal faces of the garnets, indicating these garnets grew within this matrix of finer grained material. Now I'm going to take you on a short, quick field trip to Greenland, where I'm standing in Nuuk, looking towards the Isua Gneiss granitic complex. That can be seen here. It's in southwestern Greenland, and it consists of Mesoarchean gneiss and granite terrain. This ultimately includes the Istaq Gneiss Complex. So we can see the city of Nuuk here. It's surrounded by these ancient metamorphic rocks that range in age from about 3.7 to 3.8 billion years, some of the oldest rocks on Earth. I got to meet the mayor of Nuuk while I was visiting. He handed me a cigarette lighter that says Nuuk on it, a sealskin wallet, and something else I can't remember right now. When I used the sealskin wallet briefly, the fur came off in my pocket, so I gave it to my brother for Christmas. I think he noticed that too. And here we have the gneiss appearing in town. This is one of the housing complexes there. Nuuk is known for being the most indigenous of all cities, about 90% indigenous Greenlandic population occupying Nuuk. So you can see the coarse banding here, the foliation of light and dark colored minerals. Just another look here along the shore. Again, very distinctive looking rocks, very nice looking gneiss. And moving into my former kitchen in Saskatoon, where I purchased migmatite for countertop. And what you'll see most notably here are again garnets. You'll also notice the shine due to the micas, and you can see some little blebs of different feldspars and quartz in this rock. So this rock was partially molten. Get a little better feel for that here, where you can see deformation of a band due to movement, due to compression of this rock. So these metamorphic textures provide us with a means to classify foliated rocks. They define metamorphic grade, crystal size, type of foliation, and banding. The nomenclature of foliated rocks is going to be slate, phyllite, schist, gneiss, and migmatite. And here we have the end members: slate, schist, and migmatite. Alternatively, non-foliated rocks are known as granoblastic rocks. These are the non-foliated metamorphic rocks composed mainly of crystals that grow in equant shapes such as cubes and spheres rather than platy or elongate shapes. The nomenclature of granoblastic rocks includes hornfels. High temperature contact metamorphism generates a hornfel, named hornfel for its toughness, the difficulty in breaking it. Quartzites, also very hard rocks with interlocking quartz grains. They fuse together. Marbles are interlocking calcite crystals that result from the metamorphism of limestone. Greenstones are metamorphosmafic rocks with chlorite, a green mineral. Amphibolites are composed of amphiboles and pyroxenes, generally medium to high grade. Granulites or granophyls result from high-grade metamorphism of shales, sandstones, and igneous rocks. They're coarse-grained metamorphic rocks. So here we'll take a closer look at each of those metamorphic textures of granoblastic rocks, starting with hornfels. Again, these are generated by contact metamorphism. So the rocks are baked and hardened from the heat of intrusive magma bodies. They're massive, they're hard, they're splintery, and in some cases exceedingly tough and durable. They're sometimes known as ringstones that are used in turn in lithophones. A lithophone is kind of like an organ that uses stone instead of pipes, or a xylophone that uses stone instead of pieces of metal, different sized pieces of metal. So little hammers bang on these things, and you have a musical instrument that uses rocks to make the tone. Moving into Greenland, we have quartzite. This is a structure that was built in Gardar, known by the Greenlandic people as Igaliku. This was occupied over 1,000 years ago by the Bishop of Greenland, and this is the Tithe House. So this is where they stored valuables like polar bear skins and cheese. And as you can see, it's been pretty resistant to any kind of weathering over the last 1,000 years. Marble is commonly used for statuary, and the reason it's used is because it doesn't cleave and it's relatively soft. So there's some amazing artworks produced by people from this metamorphic rock, this metamorphosed limestone. Greenstones are greenish-hued metamorphosed basalt. Greenstone belts are zones of variably metamorphosed mafic to ultramafic volcanic sequences with associated sedimentary rocks that occur within Archean and Proterozoic cratons between granites and gneisses. So characteristic green color in both of these hand specimens. This is metamorphosed basalt. It's baked back to look like the original olivine. Amphibolites are metamorphic rocks that contain amphiboles and pyroxenes, most notably hornblende and actinolite, as well as plagioclase feldspar, but with little or no quartz. They're typically dark-colored and dense, with a weakly foliated or schistose structure. Two examples of amphibolites here. Granulites are high-grade metamorphic rocks of the granulite facies that have experienced high temperature and moderate pressure metamorphism. They're medium to coarse grained and mainly composed of feldspars, sometimes associated with quartz and anhydrous ferromagnesian minerals. They have a granoblastic texture and gneiss to massive structure. Many of these granulites represent samples of deep continental crust, so they give us some clues as to what's going on deep within the crust. So to break these down in chart form, we have foliated rocks that are distinguished by slaty cleavage, schistosity, or gneissic foliation. Mineral grains show preferred orientation. The rock names are slate, phyllite, schist, and gneiss in that order of increasing metamorphism. Typical parent rocks are shales and sandstones. Alternatively, granoblastic rocks are non-foliated. They're granular, characterized by coarse or fine interlocking grains with little or no preferred orientation. Rocks include hornfels, quartzite, marble, argillite, which is baked clay, greenstone, metamorphosed basalt, amphibolite, which can come from metamorphism of shale or basalt, granulite, which comes also from shale or basalt. Porphroblastic metamorphic rocks are large crystals set in a fine-grained matrix. These can range from slates to gneisses, and the original parent rock is usually shale. So shale consists of clay minerals that are aluminum-rich. When you bake those aluminum-rich minerals, you get garnets, as one example. Now we can look at regional metamorphism and metamorphic grade as being intertwined, closely related. The grades of metamorphism include low, intermediate, and high, and these generate mineral isogrades, zones of change. Really, it means zones of similarity. Index minerals are going to reflect pressure and temperature conditions. These are the geobarometers and geothermometers that we discussed previously. Usually groups of 2 to 3 index minerals are used to form an isograde. Here we have an example from the northeastern United States where after continent-continent collision, we have increasing metamorphism as you approach that collision zone. So out here, the non-compressed, non-heated rocks are non-metamorphosed. As a rind around that non-metamorphosed material, we have the chlorite zone, so greenish metamorphic rocks. They're going to transition into the biotite zone, slightly higher grade, where biotite dominates, then into the medium grade metamorphic rocks that include the garnet zone, staurolite zone, and ultimately the highest grade metamorphic rocks displayed here in this region are known as the selimonite zone. The selimonite zone is named after a particular lath-shaped clear crystal that looks like quartz, but it's not quartz. We're using index minerals here to define metamorphic zones. Presenting this in another way, we have the increase in pressure in kilobars along this axis, increase in temperature along this axis, and depth, which is associated with pressure on this axis. Starting out at low temperature and low pressure, we generate slate. Turn up the heat a bit, we begin to produce micas, and the rock becomes shiny. It becomes a phyllite. Now, if we maintain the same trajectory in a subduction zone, for example, we enter the intermediate grade range or zone in which schist is produced. Continuing further, increasing temperature and pressure, we generate gneisses and ultimately migmatites when some melting has occurred. Alternatively, if the pressure increases but the temperature does not, we can transition from low-grade phyllites to blue schist. And a blue schist is just that. It's a blue schist. It tends to be harder, though. It doesn't split as easily, at least in my experience, as your intermediate grade traditional schist. Just taking another look at mineral composition. As we increase metamorphic grade, at low grade, we'll generate chlorites and white micas, generally muscovite. Intermediate grade igneous rocks produce biotites, garnets, staurolites, and kyanite, two very distinctive metamorphic minerals, as is garnet. And then ultimately at the high granulite phase, we see the precipitation of selimonite. And albite is going to form throughout this low to high grade sequence. This is a sequence for metamorphism of shale. If we start out with a mafic rock, say a pillow basalt, and we heat and increase the pressure on that pillow basalt, again, we're going to generate low-grade chlorite rocks. At very low temperatures, we'll generate zeolite, which are a weird class of crystals that are used for water purification, and Bosch is starting to use them in dishwashers because of this phenomena of generating or releasing heat depending on whether they're wet or dry. So that's kind of a cool thing. There's some vague potential for using it to heat buildings. So as we increase the temperature and pressure, we go into the production of epidote and amphiboles, ultimately into garnets and pyroxenes. The transition here at low temperatures will be from sodium-rich plagioclase feldspars to calcium-rich plagioclase feldspars at higher temperatures, just like we see in Bowen's reaction series. Now the metamorphic facies, green schist are going to result from the production of muscovite, chlorite, quartz, and albite. If the parent is basalt, we'll generate albite, epidote, and chlorite. If the parent is shale, and we're in the amphibolite phase, we'll generate muscovite, biotite, garnet, quartz, albite, staurolite, kyanite, and solomonite, whereas metamorphosed basalt would produce amphiboles and plagioclase feldspars. In the granulite facies, again, the minerals produced from a shale parent would include garnet, solomonite, albite, orthoclase, quartz, and biotite. Basalt parent would generate calcium-rich pyroxene or calcium-rich plagioclase feldspar, known as ornorthite. The eclogite facies from a shale parent will generate garnet, sodium-rich pyroxenes, quartz, coesite, and kyanite. Basalt parent will generate sodium-rich pyroxenes and garnets. Now, putting all that together in this diagram, it's a slight variant of the one we saw a few minutes ago. Again, zeolites, the weirdo minerals, are going to form here at low pressure, low temperature. If we go down into the subduction zone without increasing temperature much, we go through the blue schist phase. Alternatively, increased temperature, we go into the green schist phase, and increasing temperature and pressure further, amphibolite, and then into granulites. Hornfels are going to be generated by contact metamorphism, and therefore they're going to occur at shallow depths and shallow pressures because this contact is going to take place in that environment. It's essentially just baking the rock by being in contact with it. So these metamorphic facies are going to correspond to particular combinations of pressure and temperature, and they're used to indicate specific tectonic environments. Also happening during metamorphism is we can introduce some new elements to the mix. Some of these new elements are very strong color generators or color centers. The introduction of these metals is going to dramatically change the color of the ultimate minerals that are generated. So metamorphism occurs in or near plate interiors. We can see that in places like Yellowstone Park. At divergent plate margins, the mid-ocean ridges. At convergent plate margins, where we push two continents together, Himalayas being a good example. Transform plate margins, such as the San Andreas Fault in California, where rocks are sliding past each other, introducing pressure and some slight increase in temperature perhaps. So ultimately, tectonic transport can move rock through different pressure temperature zones. So we start out with a rock here. This exotic terrain is colliding with continental crust. Our mineral is going to start to go down the subduction zone. So temperature and pressure is increasing, and then as the minerals continue to grow, the crystals increase in size, they're going to get pushed up. So there's going to be some pressure involved in this, but the pressure ultimately decreases as that rock reaches the surface again. Temperature is likewise going to decrease. So we see a change from low temperature, low pressure to high temperature, high pressure, and then low temperature, low pressure again. So this gives us a history of burial and exhumation. In the example here, during metamorphism, a garnet crystal is growing, and the composition of the growing crystal is going to change as the temperature and pressure around it change. So we start out in that exotic terrain, we force it down the subduction zone. This mineral is going to grow as it travels down into a zone of higher temperature and higher pressure. And then we're going to turn that whole thing around and uplift this mineral. It's still hot, it's still under pressure, so it's going to continue to metamorphose, but at lower temperatures and lower pressures. So the resulting new material is going to be representative of that. So we can use this zoning of a single crystal to reconstruct the history of that block of rock. So this is known as prograde and retrograde paths. Here in this diagram, we start out with a slate. We're going to force that slate down the subduction zone, increasing temperature and pressure, turning it into phyllite, schist, a gneiss, And then we start to exhume that material, and it begins to back precipitate in an accretionary fashion, precipitate lower grade metamorphic material on top, ultimately resulting in a low grade rind around a high grade center. This garnet crystal initially grows in a schist, but ends up growing in a gneiss. And we can see that that can happen in different scenarios. If we have a steep pressure gradient, but shallow temperature gradient, we're going to experience low temperature, high pressure metamorphism within a subduction zone. So think blue schist in this case. The pressure is increasing dramatically, but the temperature isn't. Conversely, by forcing material down to a shallow depth, we're going to increase the temperature, but not so much the pressure, not as much as or as quickly as in this example here. So this is a high temperature, high pressure metamorphic belt within a mountain range. And we can see that the prograde, retrograde path here differs dramatically from that here. Again, we never get to really high temperatures in this scenario, whereas in this scenario, we can get right up to the migmatite facies. Ultimately, plate tectonics and metamorphism are intimately intertwined, where rapid erosion or exhumation rates of mountain ranges show a relationship between tectonics, also known as orogeny, climate. The more brutal the physical weathering, the faster you're going to exhume that rock. Ultimately, this controls the flow of metamorphic rocks to the surface.
That's it. That's all I have to say about that.